So maybe we'll start with the revision of previous class, and if somebody is running late, they can join us on the way. So we are again working with Podzar, but I think in the next class we'll look at Cheng as well. So I have been using Cheng for Smith charts, and today we'll start with the new module in the second half of the class, and that will again involve some Smith charts. So right now, the previous class we were doing module 5. We will finish module 5 today and start with module 6. So module 6 is impedance matching and tuning. So we are almost halfway through the course. Maybe a few more classes, and then we'll wrap up with the this course, which will cover all the passive things from Podzar and like in general RF and microwave. In the last class, we discussed the impedance and admittance matrices and the scattering. We started with the scattering matrix. So we saw what was scattering matrix. A few properties we'll see today. So starting with the recap. So in the last class, so about the impedance and admittance matrices. So essentially, we take an n-port network, and at the ports, we take this reference planes, and at these planes, we measure we quantify the in, incident voltage and the reflected voltage and the incident current and the reflected current. We do this for all the ports, and we use these values to get some quantifiable create matrices which helps us to solve the problems. So if you have a matrix for like a particular system, then you can do mathematical operations on them, and it makes the problem simpler. So this is how we form the matrix for an impedance or the admittance matrix. So what we do is we write down the voltages in terms of the currents, and then we form these matrices. So the Z11 is basically the impedance transformation between port for the port 1 itself, and Z12 is impedance transformation between port 1 and 2, and similarly this goes on. So this is we discussed all this in the last class. So this Z and Y are the impedance and admittance matrices, and they are inverse of each other. We looked how we calculate the individual entries of these matrices. We have we make the currents and voltages zero at for different values, and then we solve for them. So I think the all these things are mentioned in the slide, and also like all these things have been borrowed from Podzar. So you can refer to either of them to revise. We also did some small numericals for the evaluation of impedance parameters. So basically what we were doing was we were either short circuiting or open circuiting the either ports, and then calculating the impedances. That's all we try to do. And then we start looked at the scattering matrix, which was essentially a relationship between the input and output voltage, like the incident and reflected voltages. So we were we on the left hand side we had the reflected voltages from the at the different ports, and on the right hand side we had the incident voltages at the different ports. And this transformation allowed us to get the values, get the value of the reflected wave at a port if a certain wave was incident on a different port or at the same port. And this is how we calculate the individual entries for this matrix. And then we looked at some salient properties of this the S parameters. So essentially the SII is the reflection coefficient of the ith port, and Sij is the transmission coefficient between port J to port I. We also looked at this example, so I won't go into detail today. So you can read this, and if you have any doubt, we can discuss. And then we looked at the finding out the S parameters if we had the impedance matrix. So we derived this relationship, and So for example, if you had the S if you had the Z impedance matrix, that is the Z, and you wanted to calculate the S parameter, this is the relationship how you'll do it. So you take the Z matrix, add it to an identity matrix, take the inverse of the whole thing, and then multiply it with the difference of the Z matrix and the identity matrix, and this will give you the S parameter. So all these matrices that we're looking at, the Z matrix, Y matrix, S matrix, and today we'll look at the ABCD parameters of the transmission matrix. All these can be calculated from each other, and a table for two-port element, the two-port matrix, sorry, two-port system is also given in the POSAR in I think some table. Okay, I have also included that in the slide as well. Now, we also looked at what happens if the system is reciprocal or it is lossless, and if they are both. So in that case, we have certain properties that we can use for the S parameters. For example, if it is symmetric, the S matrix will be matrix will be also symmetric. For reciprocal networks, it will be symmetric. And this essentially says that we have lesser unknowns to solve for. The You only need to solve for the top half of the matrix, and the bottom half, like the if you cut the matrix diagonally, then half of it is already known. And similarly, if they are lossless, the matrix turned out to be unitary. So this observation gave us these particular relationships, which allowed us to from this essentially we say that if we know the S parameters, the S matrix for a certain network, then we can basically solve this relationship and say whether the system or the network is lossless or not. Then we saw a few more examples. So today we'll start here today. So some more properties. For example, a shift in reference plane. So so essentially this is not very difficult thing. So this you can, for example, if you are solving a particular problem and you want to get the S parameter in a system from you know the S parameter at a certain point and you want to know the S parameter at a different point. So you can do it anyways, like using simple maths, but like we'll discuss it if you want to know the process for doing this. So essentially, very close examples for this is when, for example, you are doing measurements in the lab and you are using a VNA, and you measured your S parameter of a device using some cables, and your VNA was calibrated let me just maybe draw this. So I think this thing can be used in this particular example. For example, you had you had a VNA, right? So S parameters are usually are measured by VNA, vector network analyzer. And for example, what we do is before measurements, we calibrate the VNA. And for just say that you calibrated the VNA for ports over here. And then while measuring, you forgot and you had a device which had its two ports over here. And between these two ports, you use some cables. Now, so in this case, what happens is your reference plane was initially over here. Okay, so this is getting scribbled. So for example, the reference plane was near the where did it go? The reference plane was near the VNA, and while calibration, and now what happened was that you measured it through the cables, and now you have to calculate the S parameters of this device. But what happens is when you calibrate the VNA till this point, the VNA will give the S parameters of this entire thing, whatever is connected between these two ports. So what you can do is you can use this reference plane technique, and if you know that your cable is lossless or has very low loss, then you can simply use this method to get the S parameters of your device under test. So just consider this N-port microwave network, and this you have the reference plane initially over here, which is Zn equal to 0, and now the plane where you want to shift the S parameters, the new S parameters where you need is at Zn equal to Ln. So this Ln is the new position where you want the reference plane, and now you have the incident and reflected voltages given by V1 plus and V1 minus at the first port, and similarly for nth port it's given by Vn plus and Vn minus at the plane Zn equals to 0, and at the new reference plane where you want to shift it, over there it is given by Vn prime V prime n plus or V prime n minus, and similarly for all the ports. So so we have denoted the reflected and incident voltages at the different at both the old reference plane and the new reference plane. And let's just say we know the S parameter of the input network at this particular plane over here, and now we want to shift it to here. So this is the S parameter if we were measuring over here, and the S prime is the S parameter if this entire thing was under consideration. So maybe I'll again try to draw it. This is not very helpful. So S prime is essentially the S parameter for this entire network. For example, so we are including this device under test and the this lossless line. So this is S prime, and if we were measuring just till here, this would have been S. Okay, so maybe my attempts at drawing are not very fruitful. So anyways, essentially what I'm trying to say is this entire region is for the S prime, and this the only the S parameter for the device is S, and with the cable it is S prime. So if we know this S and we want to calculate the S prime, and we're now denoting the total thing as S prime. And in terms of incident reflected voltages, we can say that that this V minus is equals to S into V plus. So essentially, we are saying that at this particular port over here, we have this relationship. The reflected voltage is equals to the S parameters into the incident voltages. And at this particular point over at this reference plane, we have V prime minus is equals to S prime V prime plus. So the V prime minus is the reflected voltage, and V prime plus is the incident voltage at the plane over here, and this total thing as parameters given by S prime. So so this is clear, and then okay, maybe instead of me saying this is clear, I can like if you are you able to follow what we are trying to do over here? Um, how we got like this about the this S and S prime. Was I able to explain this? If you have any doubts, maybe I'll let you read this. Okay, I hope you got the time to read, and if you are not able to follow, you can just type in the chat. So once we have the this relationship between V minus V plus V prime minus and V prime plus and S prime, the next thing we do is we calculate the relationship between V prime plus and V prime plus and V plus. So so essentially, if we are considering this line, this transmission line as lossless, the only thing that will affect is the phase shift over here in between these two planes. And we can give the phase shift with this term over here, e power j theta n, where theta n is beta n ln, and this is the propagation constant, and this is the length of the shift of the reference plane. So this is how these two terms are related, the v and v primes. And what we can do is we can use this information and substitute it back over here to get the relationship between v prime and v prime minus and v prime plus. Uh, uh, so what we have done is we have used this information in the first equation over here, and doing that we have got this relationship over here. So on both sides, since these are all diagonal matrices, so the phase shift terms appears in the diagonals only. So okay, so we got the so we had this information, and doing using that we have this relationship now between v prime minus and v prime plus and s over here. And now what we can do is we can solve for v prime minus by bringing this matrix on the right hand side, taking its inverse, and its inverse will look something like this. You can verify this. And then what we know that is the ratio of this v prime minus and v prime plus is essentially s prime. And so now we have the relationship between s prime and s, and which is only dependent, which has these two new matrices added to it. And then we can write this from the matrix form to just this each element. For each element, the it will be given by this expression over here, where this SNN is the SNN prime is the entry, each entry of this S matrix over here. And uh, um, which is essentially equal to this term over here, where we have e power minus 2j theta n. So this just says that the diagonal elements only have suffer a phase shift of 2 theta n. So effectively, we can like, it is also visually it can be seen that the wave will travel from this direction, in this direction once, and in the reverse direction again. So essentially, this path will be covered two times, and which is given. So this will incur the phase shift twice of theta n. So I hope you were able to follow. I can repeat this. Maybe okay, I'll pause over here and let you read the slide. So this summarizing what you have discussed now. If you have any doubts, you can like unmute yourself and say, and or write in the chat. Otherwise, we'll move forward.
So you're in mute.
Yeah, thanks. Yeah, thanks. I forgot to unmute myself. Okay, so up till now, what we were looking at was the S parameters discussions were being done, where regarding considering that there were no losses, like the S parameters that we calculated for these systems, they were lossless, and now the Podzar has this section for generalized scattering parameters, so we'll look at that. So over here what we are doing is we again we are okay, so let us look at what we have done till now. So we had the voltage and current expressions like this, and the incident and reflected voltage is given as this, and the power can be calculated using this expression over here, where we had these terms as pure imaginary. So essentially, the power at the load was given by this expression. So this is basically the incident voltage minus the reflected voltage is the power dissipated at the or power delivered to the load. Now the net power. So this is all fine, but this result is only valid when the characteristic impedance is real, and it does not apply when Z naught is complex in case of a lossy line. So if our system had a lossy transmission line, or what our system is lossy, then this analysis would not work. And so we now define a new set of waves called power waves, which has useful properties when we are when we are dealing with power transfer. Now, what we do is we bring in two new alphabets, uh, A and B, which are describing the linear transformation. So these are essentially unitless quantities given. So A is given by V plus ZR I divided by 2 root RR, where ZR is essentially the reference impedance, and it could be complex. Okay, so reference impedance is essentially your the impedance at the ports. Now, once we have defined these quantities, so you'll have to bear with me that these quantities we have like this. This is not a real thing. We are just introducing them, but this will help us for lossy transmission line and lossy systems as parameters. Now, using this A and B, we can again define the voltage and current in terms of these two quantities, and and now we can find out the power delivered to the load using in terms of A and B. And again, this term is now purely imaginary, so we ignore them when we remove this real function over here. So this property comes from the complex numbers. So now again, A is essentially the power incident power, and B is the reflected power from at the load, and so this is and the difference gives us the power delivered to the load. So now this particular result is valid for any reference impedance ZR. So we introduced this ZR over here, and now since this the input impedance is now ZR, this is complex. So and the imaginary part of the complex term refers to the loss. So this is okay, and this result is valid for any reference impedance ZR, and essentially for the lossy cases as well. Now, we can also calculate the reflection coefficient using these terms, and this is given by the ratio of B by A. And now this V over here is essentially the voltage at the load, which can be given by ZL into I. And so hence this you can see this particular formula resembles to one which we already know. Just in case of Z naught, we have this ZR, which is the reference impedance over here. And again, the reflected wave will become zero if if ZR becomes equal to this conjugate term over here. So essentially, if this becomes zero, will have zero reflections from the load. So this is something that was important to be included over here. And now, once we have seen the this A and B, now this we can now define the generalized scattering matrix for this particular case. So whatever this the A and B expressions, they can be written in form of matrices, where we have like F, and this F is introduced over here, where F is a diagonal matrix with with entries as half real part of ZRI. So this denominator thing became this F matrix. We have V, we have I, and we have ZR. So A and B are written now in matrix form, and the impedance matrix relationship gives V is equals to Z into I, and we can then rewrite this entire thing as over here. So we are writing this like this is simple substitution and things, and then the ratio of B by A is essentially gives us the power waves, the scattering matrix for the power waves. So like like this is new to me as well. Like I've not used this particular relationship till now, but maybe when I'm also I'll also deal with lossy cases, this will be useful. So in general, mostly like when we are working with passive devices and like we are fabricating stuff, we use like materials with very low loss, and we do analysis considering them as lossless, and then we account for the imperfections to the losses. But if you come across a device which is lossy, or maybe this analysis will be very helpful. And again, so one thing that has to be noted is that to find out this scattering matrix for power waves, the procedure will be to find out the Z matrices, and then calculate like this this scattering matrix for the generalized scattering matrix. So so you'll need to find out the impedance matrices first. Unlike the you cannot find out the this generalized scattering matrix from the scattering matrix that we have seen earlier, where we were calculating them as a ratio of incident and reflected voltages, and for that we were making open circuits or short circuits. So this is this to find out this matrix, the procedure will be different. Okay, so this is all for the part of scattering matrix. Maybe I'll take a pause over here so that you can absorb and reflect what we discussed, and then we'll start with the ABCD parameters. So that is the fourth type of matrix that we'll see from this particular module, and then after ABCD parameters, we'll move to the new module. Yeah, so if you have any questions, maybe we can take now from the scattering matrix part. Well, I'll pause over here and let you think. Okay, so we'll start with the transmission matrix. We also call this as ABCD matrix because the entries of this matrix are ABCD. So essentially, this is the most popular type of matrix among us if we are dealing with two-port networks. So the thing is, they provide very easy calculation for if you are dealing with a network which has a number of components like cascaded. So in that case, what you can do is if you know the ABCD parameters of a network, and if you have two such networks attached to each other, cascade in the cascade form, you can just multiply these matrices to get the ABCD parameter for this entire network. And now since the information is usually carried by the impedance matrix or the admittance matrix or the scattering matrix, we have transformations which can convert the ABCD matrix into the said type of matrix, for example, the S parameters. So well, but the limitation is that the ABCD matrix can be only used for two-port networks. So, for example, if you have a multi-port network, you might have to match the other ports and convert it to just a two-port system, or break the system into a number of two-port matrices, a number of two-port networks. And the S, Z, and Y, they can be used for any number of ports. But since the ABCD matrices allow us easy computation, so these are used very frequently. So, for example, I'll give you an example. For example, we need to find out the S parameter of a network which has an element like this, and then there is an element like this, and then there is some other network which has two types of. So these boxes can be of any type of element. For example, this could be an inductor, capacitor, irrespective. So again, if there is an network. For example, this is your entire network, and these are all connected, right? And you need the S parameters of this entire thing. So what you can do is if you have the S parameter of the individual uh, these individual networks, you can convert them to the ABCD matrix, and um, so for each of the for each of this network you can. Yeah. So if for each of this network, you can convert the S parameter. Since you must know the S parameter or Z parameter, whatever Z, Y, or S, you convert them into ABCD matrix, and note that all of them are two ports. So once you have converted them to in the ABCD matrix, you can just multiply the matrices in the order which they appear. So you cannot change the order in which they are multiplied. And once you have multiplied all these matrices, you'll get a final ABCD matrix, and you can convert that ABCD matrix into the S matrix or Z matrix, whatever you need, and you can get the S matrix for the entire system. But if you had to directly calculate the S matrix for this complicated circuit, it will be more stressful for you. So going through this ABCD path makes it easier. Now, the relationship between the like how do we calculate this ABCD matrix? So what we have done is we have I1 V1 at current at the port 1 and I2 V2 current at port 2. Note that the direction of I2 is different from the direction of I2 that we had in ZY or S parameters. So this is we have once we have defined the voltages and currents at the ports, we give the relationship as V1 is equals to A V2 plus B I2, and I1 is equals to C V2 plus D I2, and using this we can write them in the matrix form where V1 I1 is equals to A B C D matrix and multiplied by V2 I2. So, and this is essentially the relationship between the input voltage and current and output voltage and current in terms of the ABCD matrix. Now, what as I was saying earlier, so for example, once we have defined the ABCD parameters for this network, similarly we can do the ABCD parameter for this network as well. So for this network, I2 and V2 are the input voltages and current, and I3 and V3 are the input the voltages and output voltage and currents. Now, once so we have this relationship as I2 V2, I3 V3 over here, this I2 V2 and I3 V3 over here, and V1 I1 and V2 I2 over here. Now, what we can simply do is we can use this value, substitute V2 I2 from here over here. So we get this final relationship between V1 I1 and V3 I3 over here, and we can simply just multiply these two matrices, and so we'll after multiplication we'll get for example a matrix A3 B3 C3 D3, and that particular matrix is essentially the this transmission matrix or the ABCD matrix for this entire network. So, as I'm trying to say is that we can just consider this entire thing into one system and with one network, and for that the ABCD network ABCD parameters will be given by the product of this matrix over here. So in words, the ABCD matrix of a cascade connection of two networks is equal to the product of the ABCD matrices representing the individual two ports, and this can be done for any number of the cascaded networks. And one thing you must remember, the order of multiplication of the matrix must be the same. So you just cannot multiply keep this matrix over here and keep this matrix over. You cannot do that because matrix multiplication in general is not commutative. Commutative means like for like simple numbers, AB is equals to BA. But the same will not happen for a matrix. So this is not true for matrices. So I hope you were able to follow this. Maybe I'll take a pause over here and let you read this. Please let me know if you are not able to follow or if you have any doubts. Okay, so we'll proceed then. So here, like this table is also present in Poser. So this is essentially a list of ABCD parameters for different like very common two-port networks. For example, if you have a series impedance or a shunt admittance, um, a transmission line with Z naught and beta as their characteristics impedance and the propagation constant. So this is a lossless transmission line. And for example, like an a transformer with n is to 1 coil ratio, the a pi network or a T network. So for each of these cases, we have A, B, C, D defined as volume. So the good exercise will be to try to derive them by yourself. But if you remember this, this will help you in solving problems very quickly if you memorize them. But it's not necessary because it can be derived anyways. For example, like these two will come in handy if the circuit is a bit complex than this, but otherwise, this even this circuit can be broken down into the first two elements over here, these two circuits. So you can see like how easy this becomes if you know this ABCD parameters. Okay, so we'll do a simple like example. For example, the first entry in the table where we have to calculate the ABCD parameters of a two-port network consisting of a series impedance Z between ports one and two. Okay, so essentially, so this is the circuit, and just imagine that this Z is over here. Now, we know the relationships that V1 is equals to AV2 plus DI2 and I1 is equals to CV2 plus DI2. Now, to calculate, for example, A is given by V1 by V2 when I2 is equals to 0. So, I2 will be 0 when we make this as open circuit. So, in case of open circuit, what will happen is whatever be the V1, this V2 will be the same for this particular circuit. So the potential over here will be same as the potential over here, and this turns out to be 1. Now similarly, to calculate B, it is V1 by I2. So V1 by I2 when V2 is equals to 0. V2 is 0 when this is short circuit. So in that case, the voltage we give over here will and the current I1 will be equal to I2, and this current will be equal to V1 by Z. So this will the I1 equal to I2 is equals to V1 by Z. So and yeah, so we substitute I2 is equals to V1 by Z, and we get B is equals to Z. Similarly, for C and D, we can solve. For example, if we are looking at C, we have to make C is equals to I1 by V2 with I2 equal to 0. So I2 is 0 when for open circuit. When it is I2 is open circuit, um, I2 is 0 when this is open circuit, and when I2 is 0, I1 will also be 0. So C will be 0, and D is equals to I1 by I2 when V2 is 0. So when V2 is 0, for in this case, current I1 will be equal to I2 in any case. So we have I1 by I1 equal to 1. So this, so we have found out the ABCD matrix for this particular series impedance. So I let you read this because I just read this out very quickly. So please let me know if you are not able to follow this example. Okay, so I hope this was simple. In this way, you can try for all the things that were listed in that table. It will give you a little confidence into solving these networks. Now, as I said before, that these matrices can be calculated from each other. So if we look into how the ABCD matrix can be calculated from the impedance matrix, or how like the dependence between them. So once you know the for example the impedance, if we have calculated the impedance matrix already, and we know that the impedance matrix are given by this relationship over here, where v1 is equals to I1 times Z11 minus I2 times Z12, and V2 is equals to I1 times Z21 minus I2 times Z22. So this is the relationship, and we know how to calculate ABCD in these cases. So now A1 is given by V1 by V2 at I2 equal to 0. So in that, for that case, we can write V1 is equals to I1 Z11, because I2 is 0 over here, and V2 is equals to uh, I1 Z21, because I2 is 0 over here. And this I1s cancel out, and we get Z11 by Z21 is equals to A. Now, similarly, we can calculate B, C, and D for like give for knowing these values over here. We're just substituting whatever needs to be 0 and for the value, and we can get A1 equal to this value, B is equals to this thing over here, Z11 Z22 minus Z12 Z21 by Z21, and C is equals to 1 by Z21, and D is equals to Z22 by Z21. So this is what you'll get. So this is just maths. Just looks troublesome, but once you know this is fine. So this is the relationship between the impedance matrices. And similarly, you can calculate the Z11 in terms of ABCD. So all this thing is listed in a very big table in Podzar. So you can refer to them while solving numericals. I believe most universities give them as formula sheets, so you don't have to memorize them. But any case, if it comes to that, you can also derive this. You should know how to derive this thing. Okay, and now relationship to the admittance matrix. So again, the admittance matrix is given by this relationship over here. And you can use the same thing that we did in the previous slide to find out the relationship between y11, y21, y12, and y22 in terms of A, B, C, and D. Now, if the network is reciprocal, what will happen is this Z12 will become equal to Z21, or Y12 will become equal to Y21. And in that case, we can represent we can in that case we can represent a circuit in terms of a T network or a pi network. So if and this so for this, and I'll like to stress that this only happens for reciprocal networks. So we are talking about reciprocal networks where this is true. Z12 equal to Z21. So this means that is reciprocal. So these are the two type networks that we also saw in the previous table. So if you know the values, you know the values of z parameter, if you know the value of of a certain network which has this you know the z parameters as z11 z12 z21 z22, you know these values, and you can just and you don't know how the circuit looks, then you can simply make a circuit which looks like this. Okay, and remember that this Z11, Z12, they can be either inductor, capacitor, or complex, or anything. So you can you can make, model the black box in this two way, either this T network or this pi network. So you can look into more detail into this. I'll just leave this to you, so that you know that if you know the ABCD uh, parameters of a matrix, and you know that it is reciprocal, or you know that the admittance or the impedance parameters of a circuit, and you don't know the circuit, then you can make a circuit out of the parameters. So that's all. And so this And this is only true for passive devices which are reciprocal. Non-reciprocal or active devices, this is not possible. Uh, so this is the table which I was talking about. It is there in Podzar. You can refer to that. So over here are the four S parameters and the Z parameters. So S parameters in terms of S parameters, very simple. S parameters in terms of Z parameters, you can see S11 is given by this expression, S12 this expression. So you can use this table to calculate like convert any parameter sz or y to sz or y. So this marks the end of our module 4, I believe, or 5. Yeah, so the yeah, I believe module 4. So any questions from what we covered till now? The next will start with impedance matching and tuning, the new topic. So essentially, so there are few more topics in Podzar which I have not included in this particular course. So they are pretty advanced for undergraduate, although knowing them is always helpful. So you can always refer to them and reach out to me if you have any doubts. So no worries in that. But to keep this course compact, and we have already lost a lot of time because me being not available. But yeah, you can refer to them. But the important things have been covered. That is the four matrices that we frequently use for microwave circuits. So we're starting with the new module now, which is impedance matching and tuning. Very important. So up till now we were looking at different theories for microwave circuits. Now we're starting with the implementation part. So we have gathered knowledge about different analysis things for the microwave circuits. Now we will use them for more practical purposes. For example, impedance matching and tuning. So all circuits in my like whatever like if you're an RF or microwave engineer, whatever your circuit you are making, you have to ensure that all the all the different parts of your circuit are impedance matched. Otherwise, what will happen is if your source is not matched to the transmission line or the transmission is not matched to the load, a lot of power will be reflected back towards the source or be lost in the circuit, and which is not ideal. So we always aim for ensuring the maximum power transfer between the source and the load. So impedance matching is essentially basically, in summary, it looks like this. So you have a transmission line which is ending at a load, and what we do is if the transmission line's characteristic impedance is not matched to like not same as the load impedance, what we do is we introduce this matching network over here, which tries to match the load impedance at a particular frequency or a number of frequency or a band of frequency. So depending upon the problem statement, so also a very active area of research in RF and microwave. A lot of people work on this matching networks. So we'll look at the popular basic theories that which is out there. Now, one thing. So what we try to do is essentially when we introduce this matching network, what we are trying to do is we are trying to like minimize reflections from the load, and obviously there will be a lot if there is impedance mismatch, there will be a lot of reflection, and the multiple reflections will be there. And when what we do is we introduce a matching network which provides certain impedance between these two impedances, and we try to tune it. So this process of introducing this matching network to minimize the load, minimize the reflections from the load, is called tuning. And why we are trying to do this is because like there are three reasons. For example, if somebody asks you, we're trying to deliver maximum power to the load, and this will happen when the reflections are minimized, and the line like the impedances are matched. The second is we are trying to this helps improve the signal to noise ratio. Because, for example, if you have a receiver components, for example, antenna or LNA, if they are not properly matched, what will happen is this will introduce more noise into your system, and you don't want that. And so this helps improve the signal to noise ratio of the system. And impedance matching is also important in power distribution networks, such as antenna array. And like if you don't do this properly, there will be amplitude and phase errors. So that is also important. If you have ever designed an antenna, you'll know if you are designing an array, you need to feed the different elements of the array through like you have one port which is delivering power to all the elements of the array, and you just cannot just directly feed draw any trace on the PCB to feed them. You'll have to make sure that the impedances are matched, and over there, this matching networks comes into play, because most networks, like most systems, have 50 ohm output, and your array will element can also have 50 ohm as the input impedance. But you cannot split the 50 ohm into 50 ohms. The 50 ohm will be split into, for example, if you have two elements, then that will be split into, for example, and 50 ohm will be split into 25 or 25, something like that. So, and then again, you cannot feed the 25 ohm to 50 ohm directly or something. So, what I'm trying to say is you will need this impedance matching technique to match the impedances at different point in the circuit. And if it is not done properly, there will be phase errors, amplitude errors, noise introduced into systems, power loss, the reflections will be there. So essentially, this is very important. So a lot of people, like initially, you might if you ignore this, and you might end up with a circuit which is not delivering proper results. And if you don't know about this, you might be thinking that something is wrong in your circuit design, and it is actually the impedance mismatch is there. So what things that we keep into mind while doing impedance matching and tuning? For example, these are complexity. So the simplest solution is like the best solution. So you can solve a particular problem in a number of ways, and the simplest one is the best, because we don't want to overcomplicate things. For example, if you're drawing traces, and you try to minimize the length and the parasitics. Similarly, we don't want very complex designs on the PCB. We want to keep it simple, and also that will if you make an impedance matching circuit which is 3D, for example, this will be very expensive. So if you can do it in 2D, if it can be done on a PCB, it is best. And if your design is all very complex, it becomes a difficult engineering problem. So the simpler thing can be mass produced. For example, if you're trying to mass produce a certain PCB or a certain component. Now, bandwidth is a real issue, actually. So, impedance matching is used, it is very simple to do it for a single frequency. But if you're working on an ultra wideband thing or a wideband circuit, this bandwidth is an issue, and you actually have to do a lot of things to ensure to maximize bandwidth, and again that will come with a number of trade-offs. Now, implementation. Uh, for example, you want to match a 100 ohm to a 50 ohm. So it can be done in a number of ways. For example, you can use a quarter wave transformer. You can use a double stub. You can use a single stub. But what are these things that we're trying to match? For example, on a PCB, it is much easier to make a single stub or a double stub, which is an open circuit instead of short circuit. So there are a number of ways we can do it, and sometimes one method is easier to implement than the other. Now adjustabilities, and so recently a lot of papers, if you look at, will provide you the facility of reconfigurability. So you can have an impedance, you can have one circuit which can impedance match at different frequencies. So that you can do, for example, if you introduce varactors or pin diodes in your circuits, you can just bias them to so that the capacitance varies, and you can then, for example, match the circuit at different frequencies. So these are the number of things that we consider while doing impedance matching and tuning. So maybe I'll take a pause over here because I said a lot of things. So let you read this slide, and if you have any confusions or questions as about to why we are doing this, or like, or any questions that you might have from your course or previous experiences, so you can ask them now, and maybe then we can start with the impedance matching technique. So we'll look at only one technique today, which is an L section technique, which involves lumped elements. And that too will just look at the analytical approach. The next class will look at the Smith chart approach. Okay. So so four things that we are looking at while doing impedance matching and tuning, and three things, the three reasons why we're trying, why we are trying to do it. Okay, so we'll start with the first technique, which is an match, which is matching with lumped elements. We call this as L section, or you might also see. Okay, so there is one other term which I'm forgetting. So essentially, this means lumped section or lumped elements being added to the transmission line. Do not confuse with inductor. So this is not inductor. This means lumped. Just a second. Okay, so to do match the circuit, what we are doing is, it can be done in two ways. So essentially, for example, you have your load impedance over here, and you have your transmission line ending over here, and we can introduce first the we can introduce first the this series element over here, and then the shunt element, and then the load. Or we can first introduce the shunt element, and then the series element, and then the load. So and these two cases, these two circuits are used in two different conditions. The first circuit is used when the normalized load impedance lies inside the 1 plus Gx circle, and the second case is used when this normalized load impedance lies outside the 1 plus Gx circle. So if you remember your Smith chart, so in the Smith chart, we had the circle over here, right? And we had this coordinates, and we had this circle is always there. So this is always there. And so on this real axis, we had fractions written. Okay, so we had 1, 2, 3, 4, and this point was infinity, and we had 1 over here, and this was 0, if I recall correctly. Yeah, so the 1 was here, 2 was here, 3 was here, and so on in this direction. And we had point 1, sorry, yeah, 0.1 over here, 0.001 over here, and similarly. So essentially, what I'm trying to say is r equal to 1 circle was here, and what we uh, what we do is to calculate ZL. So we have the big ZL with us. Okay, yeah. Think yeah, we have ZL with us, and then we divide this ZL with my God. Okay, so I'm not able to write this. So we divide this with Z naught of the characteristics impedance of the transmission line, and then so we normalize it, and after normalizing, it will either be equal to 1, 0, or 1. So so for 1 you can use so for 1 is it essentially means that the load is matched, and if it turns out to be less than 1, it will lie outside the circle, and if it is greater than 1, it will lie inside the circle. So if it lies inside the circle, we'll use this circuit over here, and if it lies outside the circle, we'll use this circuit over here. And this 1 plus Jx circle is essentially this circle over here, which is r equal to 1 circle. Okay, so okay, this text just says whatever I just said now. So 1 plus Jx circle is the resistance circle of the impedance Smith chart, for which r is equals to 1. So r equal to 1 circle, and yeah, so you normalize this, and if it lies inside, you use the A circuit. If it lies outside, you use the B circuit. And again, so this X and B can be either inductor or capacitor, and this will depend upon their uh, this will be depend upon their value. So if it is plus, it is inductor. If it is minus, it is a capacitor. So we will calculate X and B without assuming they are inductor or capacitor. Once we get their values, we'll come to know whether it is a capacitor or an inductor. So I'll pause over here. If you have any doubts, you can ask now. Otherwise, we'll proceed to looking at how the analysis is done for this circuit. Okay, so yeah, I think I missed this during animating in this slide. So just ignore this for time being. So let us consider the first circuit and do its analytical solution. So for the first circuit, let the load impedance be given by as RL plus JXL. RL is the real part and XL is the imaginary part of the load impedance. Now it is stated that this particular circuit is used when ZL is equals to ZL plus ZL by Z naught. We are normalizing it, and the small ZL lies inside the 1 plus JX circle on the Smith chart. So this will happen when RL is greater than Z. So since we don't have a Smith chart on hand with us right now, so we can just calculate, check whether RL is greater than Z naught. And if this is true, then we will be using this particular circuit. Now, once we have decided which circuit to use, we'll calculate the impedance looking for the circle. The input impedance for the circuit over here. Let me just use a pen. So yeah, so we'll calculate the Zin while looking over here. Okay, so we'll calculate Zin. Now, Zin and Zin should be equal to this Z naught. So so we have this in shunt, this in C, and these two in parallel. So we calculate the this parallel value over here and then add it to the series thing, and this should be equal to Z0 for impedance matching condition. So when we have impedance matched over here, this will be equal, and then what we do is we separate the real and imaginary parts. So and when we do that, we get this set of equations, and using this these two equations, we can like find we are removing x and like substituting x by over here in this particular equation, we can get a quadratic solution for b. So this particular expression gives us the value of b. So we have found out b, and note that this particular the input the things inside this root will always be positive because RL is greater than Z0. So RL is greater than Z0. So this will always be positive, and hence we have two solutions for b. And using the two solutions for b, we can just use the value of b in the second equation, and we can get the value of x. So we have found out the value of b and x for impedance matching condition over here. So this was pretty straightforward. You just had to this was the condition. This RL greater than Z0 is the real deal over here. If once you have done decided that this is the condition, and then you would have the circuit design with you, and all you need to do is match this Z0 equal to the impedance of this circuit, and solve for the value of b and x. And once you have b and x, your work is done. And similarly, if you have found if you checked and you found out that RL is less than Z0, then we will be using this B circuit over here. And again, we do the same process. What we do is we try to match the admittance. We try to impedance this thing. So this Z0 is over here. This Z0 is equals to this circuit over here. This is in shunt, and these two are in series. So that is correct. And using that, again, we try to find out b and x. And so we have two equations, two unknowns, and using that we can solve, and we get total this set of values. So essentially, what we get is we get total of 8 solutions, and all of them are correct. And depending upon what is convenient to you, which, for example, the lumped elements you are only available in, for example, if you're trying to get a capacitance, it will only be available into certain values. So you can use, so whichever value you find, you can use that and put that in circuit, whichever comfortable. So essentially, you have a number of solutions, and all of them are correct. So need not worry. And since RL is less than Z0, so this they are all they will all be positive. So you won't get imaginary terms coming out over here. So that is it. So okay, I'll just take a pause over here, and if you have any doubts, you can discuss now, or I'll share the slides. You can come back with doubts later as well. I hope this was fine. Today we finished with our microwave network analysis module, and we started with the impedance matching and tuning. We did the L section, yeah. So L section, yeah. So we discussed the L sections analysis part, analytical solution. We'll discuss the Smith chart in the next class, and then we'll look at single stub and double stub matching as well. For this, I'll probably use Cheng. I'll see which book has Ozar or Cheng which has better examples. I'll refer to that. And yeah, so that's all for today. If you have any doubts, you can like ask now, or we can end for today as well. Meanwhile, I'll stop the recording.